What is creep in materials, and why is it hard to analyze? Have you ever wondered why some materials seem to change shape over time, even when they are under a constant load? This phenomenon is known as creep. Creep refers to the slow and continuous deformation of a solid material when it is subjected to a constant load or stress over an extended period, particularly at higher temperatures. Unlike immediate deformation that occurs when stress exceeds a material's yield strength, creep can happen even when stress is below that yield point. This gradual change can lead to permanent shape alterations over time. Creep is especially significant in the context of mechanical failure. It can cause components to deform and eventually fail without any sudden warning. This is common in metals, polymers, and other materials that experience both heat and stress. For instance, turbine blades in engines can elongate slowly due to creep, which may lead to contact with other components and ultimately mechanical breakdown. Analyzing creep is not straightforward, and several factors contribute to this difficulty. First, creep is a time-dependent process. The deformation accumulates slowly, often over years, making it hard to predict and measure accurately in short-term tests. Second, temperature plays a significant role. The rate of creep increases dramatically with temperature, especially when the material's temperature reaches about 40% or more of its melting point. This means that the environment where the material operates heavily influences its creep behavior. Third, creep involves complex internal mechanisms such as atomic diffusion, dislocation movement, and grain boundary sliding within the material's microstructure. These mechanisms can vary based on the type of material, its microstructure, stress level, and temperature, which complicates modeling and prediction. Additionally, different materials exhibit creep in unique ways. Metals may creep through diffusion and dislocation processes, while polymers may do so through the sliding of molecular chains. This diversity requires specialized knowledge for each material type. Creep deformation also does not follow simple linear rules. It typically progresses through stages: primary, secondary, and tertiary. Each stage has different rates of deformation, which complicates analysis and life prediction. Lastly, creep can interact with other mechanical failure mechanisms, such as oxidation or cracking. This interaction can accelerate failure or alter the material's response, making failure analysis even more complex. Understanding creep is vital for designing components that operate under high stress and temperature for long durations. Engineers must consider creep to prevent unexpected mechanical breakdowns. They do this by selecting appropriate materials, controlling operating conditions, and applying safety factors in design. However, the slow and complex nature of creep deformation makes it one of the more challenging failure mechanisms to analyze and predict reliably.